Hi everyone, Mrs. Besega here, and today we're going to do the impulse momentum theorem. Impulse momentum theorem is the basis of this unit, because think about it like this. We've said that impulse, whose symbol is J, impulse is when you apply a force for a certain period of time to cause a change in momentum to an object. So one way we could calculate impulse is just doing force times time. If force is constant, I can just do force times time to get impulse. The little arrow symbols over force and J, impulse, indicate that if the force is to the left or down, I would put a negative sign for force, and that would also get a negative sign for impulse. But in real life, forces don't just stay the same value the whole time. They might start low and become higher and decrease. So if you have a force that is not constant, then you're going to need to do a force versus time graph, like the one in the center here. For that, you would do the area under a curve. But let's say you're not given a graph and you're not given a force in time. You can still calculate impulse by what's called the impulse momentum theorem. This theorem says that the impulse causes the momentum to change. So if you know the mass and velocities before and after, you can always find the impulse that created them. Notice that momentum are vectors, momenta are vectors, and therefore they get the little vector symbol over top. So impulse momentum theorem says that when you apply an impulse, that causes the object's change in momentum. So in this case, let's say I had an object with 2 kilograms of mass going 3 meters per second. Its momentum is its inertia in motion. So its inertia is 2 kilograms worth of mass. Inertia is a property of matter. So more mass, more inertia. So I'm going to put 2 in for m. This is 6 Newton seconds of momentum because it's mass times velocity. So its initial momentum is 6 Newton seconds. Then some sort of force acts on it, and I don't know what force that is. Now this 2 kilogram object is going 10 meters per second. That has gained momentum. It has sped up. Its inertia stayed the same, but its velocity increased, so its momentum increased. And now its new momentum is 2 times 10, that's 20 Newton seconds. So how much impulse acted on this? Even I don't know the force in time, I do know that it went from 6 Newton seconds of momentum to 20. And that gain must have come from the impulse. So the impulse is 20 minus 6. It gained 14 Newton seconds of momentum. This is positive impulse because it gained momentum. Let's try another one. Let's say I have an example with a cannonball. The cannon recoils backward at -2 meters per second. In this case, the cannon starts at rest. It's 30 kilograms of mass, but it's not moving, so no momentum. But afterwards, the momentum is -60. Since I'm dealing with just the cannon, the fact that the ball goes forward is a distractor, does not help in this problem. The cannon is 30 kilograms, and its final velocity is -2 meters per second. So its new momentum is -60 Newton seconds. In this case, impulse is negative. In this case, it means that there was a force acting to the left. If impulse is force times time, then that force must have been negative because our cannon went backwards. So for impulse momentum theorem, you could write this out as impulse is the final momentum minus the initial momentum. And the order does matter here, so pay attention to that, please. If you wanted to write it out more thoroughly, you could write this as impulse is the mass times final velocity minus the mass times initial velocity. This would give us our final momentum and our initial momentum. Or if you want to write it out in all its glorious detail, you could write the impulse momentum theorem is the force acting for some sort of time causes the mass to change velocity. The mass changes velocity, so the momentum changes. Now, our last and trickiest example. Let's say I have a zero point 0.6 kilogram tennis ball traveling 10 meters per second to the left. It's shown having a collision whose force and time are on a graph. So can I combine taking the area under a curve and the impulse to find a final velocity? Well, yes, I can. Let's say my tennis ball starts traveling to the left. Its initial momentum is -10 times 0.06 kilograms. So its initial momentum is -0.6. But then we have some sort of smart racket that tells us that it applies a force of 6 newtons max over a time duration of 0.3 seconds. Since it's a graph, I can't just do force times time. I need to take area under the curve. I'd be doing 1/2 a base of 0.3 times a height of 6. So this gets me an impulse of positive 0.9 Newton seconds. So I want you to think in your head what this looks like if we were doing this little momentum bar chart. The momentum starts negative and it increases by 0.9, right? So if it increases by 0.9, where does it end up? It ends up at positive 0.3. Its momentum increased by 0.9 because of the racket. So it goes from negative 0.6 to positive 0.3. What I'm picturing in my head when I do this is the fact that our new final momentum, PF, has to be equal to the initial momentum plus the impulse that acted upon it. That means if I want to calculate the final velocity, I know the mass of my object. Its final velocity would be taking its momentum divided by mass. This velocity ends up being positive because basically the tennis racket hit it so hard, it changed directions. It was going in the negative direction. It is now going in the positive direction, as a tennis ball really should during a match, shouldn't it? So to sum it up, there are 3 ways to calculate impulse. We can do force times time if the force is a constant value. We could do area under the curve if it's given a graph. But if you're given mass and both of the velocities, you can still find impulse using the impulse momentum theorem. Best of luck.